The other type of surface that's covered in section 12.6 is quadric surfaces. Now those are going to be surfaces where the cross-sectional curves that we get when we intersect the surface with a plane. And we're going to be concerned with planes that are parallel to the coordinate planes. When we intersect those surfaces with one of these planes, we're going to get a curve, and those curves are going to be conic sections. Okay, so our cross-sectional curves, and again, the ones we're going to care about are going to be in planes that are parallel to the coordinate planes. These are going to be conic sections. So let's just recall what conic sections are. Those could be ellipses, and that includes circles. A circle is just a degenerate ellipse. That could be parabolas, or that could be hyperbolas. All right, and these cross-sectional curves, another word for that is the trace. So if I were to ask you to draw a trace of a surface in the xy plane, you'd be drawing the curve of intersection of that surface with the xy plane. All right, now this whole notion of a quadric surface is going to make a lot more sense when we start looking at examples, and that's what we'll be doing in the rest of the videos for this section. What I want to do in the remainder of this video is just a quick crash course to review some of these conic sections. Now I'm going to suppose that you guys remember how to graph circles and parabolas. If not, see me in office hours immediately. All right, but I do want to just really quickly review the formulas for and the graphs of ellipses and hyperbolas. Some of you may feel very comfortable with those. If you feel like you remember the connection between the equations and the graphs of ellipses and hyperbolas and you want to skip the rest of this video, this is one time I think that could be a responsible choice. But if you feel like you need to review those, stick around and we'll go through those. Let's start with ellipses. Ellipses are going to have, as the standard form of their equation, either x minus h squared plus y minus k squared over b squared equals 1, or x minus h squared over b squared plus y minus k squared over a squared is equal to 1. Now for both of these, h, k, the point whose coordinates are the two numbers that we are subtracting from x and y, is going to equal the center. Okay. Now, these are essentially the same, except here I put a under the x's and here I put a under the y's. By definition, for an ellipse, a is going to be the bigger number. For our purposes, we don't really care. That's important if we were to care about finding the foci. An ellipse will not only have a center, but it will have two focal points. And the idea is that the sum of the distance from a point on the ellipse to each of the two focal points is constant. Okay. We're not going to need to find those foci, so this fact isn't particularly going to matter. What's going to be significant is that when the bigger number is under the x's, our ellipse is going to be wider than it is tall. And when the bigger number is under the y's, our ellipse is going to be taller than it is wide. And of course, if a and b happen to be the same, then we would have a degenerate ellipse, which would be a circle. Okay, important thing about the equation of an ellipse is that both variables are squared and we are adding them together. Standard form, it's set equal to 1. So if you have something that's set equal to 2, it's not in standard form. You'd want to just divide both sides of the equation by 2 to get it in standard form. Let's take a look at an example of an ellipse. Let's suppose I had x minus 1 squared over 4 plus y plus 2 squared over 9 equals 1. First of all, I should be able to recognize immediately from the equation that this graph is an ellipse. Both of my variables are squared, and I am adding the results. This is in standard form because it is set equal to 1. So I'm going to just write in that that 4 is 2 squared and that 9 is 3 squared. 2 and 3 are going to be the important numbers. Those are distances that we're going to be going as we draw the graph of this. I can also see from the equation that the center would be at 1, negative 2. Do remember that the center consists of the numbers that we're subtracting from x and y. So here I'm subtracting 1, adding 2 is equivalent to subtracting negative 2. So if I go to graph this, the center is at 1, negative 2. Now, I've initially plotted a point there. I'm ultimately going to erase that because the center is not a point on the ellipse. But it's helpful for me to have it right now. And then I'm going to look. Under the x's, I've got 2 squared. So because this is under the x's, that 2 is going to be a horizontal distance. So from the center, I'm going to go 2 to the left and 2 to the right. And these 2 points are going to be the points that are farthest to the left and farthest to the right on the ellipse. Similarly, because 3 squared is under the y's, that 3 is a vertical distance. So from the center, I'm going to go 3 up and 3 down, and these points are the points that are going to be highest up and lowest down. Once I've drawn those, don't really need the center anymore, so I'll erase that, and then I can just connect these points with a nice smooth curve. Point I maybe went a little too far to the right. Okay. Excellent. And you can see this is taller than it is wide because we have the bigger number underneath our y's. This is an ellipse that I would think of as being oriented vertically. Now it is possible to have ellipses that are sort of lopsided like that, so that the major axis would be a diagonal line. If we had that, what we would have is we would have some x times y's in the formula. We're not going to be dealing with that. I said we're only going to be looking at quadric surfaces where we're concerned with the cross sections in planes parallel to the coordinate planes. And the cross sections, or the conic sections that we have in those traces won't be these rotated conic sections. It's certainly possible to have those. We're just restricting ourselves this semester to looking at the nice case. All right, so that's a quick review of ellipses. Now let's take a look at hyperbolas. Now for a hyperbola, we're going to have x minus h squared over a squared minus y minus k squared over b squared equals 1, or y minus k squared over a squared minus x minus h squared over b squared is equal to 1. So the key here is that both variables are squared, but we're subtracting the results. Now again, standard form, it's going to be set equal to 1. And the rule here is not that a has to be the bigger number, but that the a squared is always under the positive term. So when I had my x's minus my y's, the number under that positive term, the x minus h squared, is the a squared. When it's the y minus k squareds that are positive and I'm subtracting the x's, the a squared is what's under the y's. All right, as with an ellipse, the center, which won't be a point on the hyperbola, but will be an important point in plotting it, the center is going to be h comma k. Now, a hyperbola is going to have 2 branches. It's either going to have a left and a right branch like so, or a top and a bottom branch like so. And the center would be a point exactly in the middle. So my hk would be there or there. So let's see if we can figure out which equation goes with which picture. Okay. If I take a look here, this can never be negative because it's a square over a square. Same thing here. The thing that I'm subtracting is never negative because it's a square over a square. But I've always got to get 1 as my result. Well, what that means is that this positive term here, the one I start with, can never be 0. If I had 0 and I subtracted something that isn't negative, there's no way I could get 1. Here, this term can never be 0, because if I had 0 here and I subtracted something that isn't negative, there's no way I could end up with 1. So if I have this sort of an equation, I know that x can never equal h, because that's what would make that initial term 0. But x equals h is the equation for the vertical line that would go through the center point. This would be the line x equals h. Here, x is never equal to h. Here, on this graph, x is h, here and here. Okay. So, if I've got this sort of an equation, I'm going to have a left and a right branch. If I have this sort of an equation, I'm going to see that y can't equal k, because that would make that initial term 0. But y equals k, that would be the equation of the horizontal line that goes through the center. Okay. So I would have something like this, where I would have a top and a bottom branch, and I'll completely avoid that horizontal line that passes through the center. Okay. So I can figure out from the equation whether I'm going to have a top branch and a bottom branch, or a left branch and a right branch. Let's just take a look at an example to see how we would graph something like this. Let's say I had x minus 1 squared over 9 minus y plus 3 squared over 16 equals 1. So I can see immediately that it's a hyperbola because both variables are squared and I'm subtracting them. This is in standard form because it's set equal to 1. I know that 9 is 3 squared and 16 is 4 squared. Again, I like to write that in because 3 and 4 are important distances that we're going to use in graphing this. Okay. So, I can say the center here is going to be 1, negative 3, just looking at the numbers that I'm subtracting from x and y. So I'm going to go ahead and plot that point. Again, once I've drawn the graph, I'm going to erase that because that's not actually a point on my hyperbola. Now, I know that a hyperbola either looks like so, with a top and bottom branch, with a left and right branch, or like so, with a top and bottom branch. I'd like to know which one I have here. Remember, this term can't be 0, because if it were, I'd have 0 minus something non-negative equals 1. That's not going to happen. So I know that x cannot equal 1. But x equaling 1 would be this vertical line. So I can never be on this vertical line, so I'm going to have a left branch and a right branch rather than a top and a bottom branch. Okay. So now I can take a look at this 3. That's going to be the horizontal distance that I go away from the center. So I'm going to go 3 to the left and 3 to the right. And that's essentially giving me these 2 points, which we call the vertices. Those are the 2 points that are going to be closest to the center. Okay. Now, I'm not going to go up 4 and down 4 to get points that are on the hyperbola. So how is this 4 useful? Well, I know I have a left and a right branch, but I don't know how tall or wide they are. I don't know whether it looks more like this or more like this. These would both be hyperbolas with a left and a right branch. What the 4 is going to help me to do is to calculate the asymptotes that I have that guide me in how tall or how wide to make the branches. So I am going to, from center, count up to 1, 2, 3, 4, but I'm not going to put a point there. I'm just going to mark off that height, and I'm going to come down 4. And again, I'll mark off that height. I'm going to just draw in this box that I've created by going 3 left and right and 4 up and down. The diagonals of that box are going to be the asymptotes for my hyperbola. Notice those diagonals will pass through this center. Notice that the slopes are plus and minus 4/3. I get rise is the number that I'm squaring under the y's. Run is the number that I'm squaring under the x's. Okay. And now those asymptotes tell me I'm not going to have a branch like so, because the branch has to approach those asymptotes. So it helps guide me for how wide that shape is going to be. I'm going to erase that center point because it's not on there. Notice the asymptotes and this box that I created, I drew as dotted lines. Totally fine to have them drawn. In fact, I may require, if you're drawing a hyperbola, that you draw the asymptotes in to show me that you've paid some attention to the scale, but they must be drawn as dotted lines. The convention is that what's drawn as a solid curve is considered to be the graph that you're drawing. Anything that you draw as a dotted line or a dotted curve is just something that you drew to help you in drawing that graph. Okay, so that's hyperbolas and ellipses in a nutshell. If you feel like you need more review of conic sections, totally fine. Let me know. I'm happy to make an appointment with you. I'm happy to talk about this more in office hours. This is as much time as I'm going to devote to it in the videos because I realize that not everybody needs that review. But particularly if you took second semester calculus a long time ago and you haven't looked at this recently and you want a little bit more practice with that, just let me know. That's totally fine.